This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay. Right. Yep, good. Okay, we're going to continue what we were looking at last lecture, which is reachability analysis. And we looked at depth first searching first, and this we sort of stopped when we started looking at breadth first searching via the symbolic approach. Now, I'm going to go over this in a bit of detail. Why? Because there's a question on the exam which will ask you to do this for a particular composed state space model of some various subsystems. So it's important you follow, particularly for the example that I'm going to do. Okay, so the idea was with the symbolic approach is that instead of enumerating every possible state, okay, so you have a big set of composed states, well, actually the states themselves, instead you can compose this set of states as Boolean operators, okay, and you can also include variables in there as well, which essentially sucks down the amount of the space that you're kind of looking over. And we'll see that when we look at an example. So the idea is at each step you're applying the state update function and you're looking at the reachable states from there. So it's like if you're in the state machine, right, you apply the update function, you then see all the states that you can see and you add them to the reachable set, right, as a set rather than as discrete individual states. Okay, so you sort of stack them up in a big set. And the algorithm in words can be written like this. So you will have to do something very similar to this, not as formally, but you'll have to go through the process on the exam. So the idea is you start off with an initial state. That's the population of your set of reached states, big R. And then what you do is you apply the update function and you add all of those states that you can see with the update function. For instance, back here, right, Q1, all those states you then add to R, the set of reached states, via a union, because we're now talking about sets here, right? So you look at all the new states you can see and you union them with what you've already seen. but you are excluding ones you've already seen, right? We don't want to union together everything, right? So anything you haven't seen. Why do we do this? Or anything we've already seen, why do we do this? Because the test to break the loop is whether or not we actually have seen anything new. Okay, so if we're doing this and eventually by excluding what we've already seen from this new set that we can see from a current state, we end up with an empty set, we know we've seen everything. Okay, so that's the way of building it up. Now, this is a very top-level description of the algorithm. It's saying nothing about this search that's going on inside here. You're saying, or the construction of the reachable, the set of reach states. Now, it's a very difficult thing to do. If you can imagine, even for a moderate circuit with, say, 1 million gates in it, maybe, and you want to consider perhaps the output of each gate as its state, it can only be 0 or 1. If it's in a simple gate, we don't assume weird values, 0 or 1, and you want to have some sort of mapping of how the state of the system evolves, and you want to see what state it can get into. This is going to be pretty messy, right? You've got 1 million gates, 10 million gates maybe, each of them has a unique state. Yikes, the reachability set's massive. So there are at least two heuristics for doing this, and they're called BDD and SAT, or BSAT sometimes. Binary decision diagrams and Boolean satisfiability. Now these are heuristics for working out what's reachable from a particular state and then adding them to the particular set that you've already seen. I'm not going to go into details about these things because they're complex algorithms, right? And even then, it's not clear which one to use. They're heuristics. So the symbolic reachability algorithm is a formal way of checking the reachability of a circuit. But the method that we actually do the scanning over all possible states is heuristic in nature. Okay? That's very different from taking a heuristic approach to reachability overall. Okay, so a heuristic approach to reachability would be chuck it in a simulation, run it a few times, and it seems to have worked. Okay, or chuck a few different conditions in, not structured, just sort of try a few things and it seems to work. That's sort of almost a heuristic way of checking the thing. This is a structured way of checking with heuristics in order to build up the set of reachable states. Okay, so sometimes that's used, sometimes that's used. You can go and Google them if you're interested. Sometimes you can switch between the two. So you could try doing BDD to build up this set. You find out it's becoming infeasible, you know, it's becoming too complex or something, so you could switch to something like BSAT as well, or start again with BSAT. So it's a tricky problem. It's known as an NP-complete problem, to be able to find the entire reachable set of states of an FSM. If you don't know what NP-complete, incomplete means, it's like the travelling salesman problem. It's similar to that, right? Where a salesman has to go and visit a certain amount of nodes, and there's costs associated with visiting each node, and you've got to find the optimal path to go amongst all the nodes. It's a difficult problem. You can find the problem, but you cannot predict how easy it is, how easy you will be able to find it, if you like. Okay, so it's what's known as an NP-complete problem. It's solvable, but it's tough to solve. It's not easily predictable. Okay, so this is doing it. The symbolic reachability algorithm does it implicitly, as we will see in the next state. Next slide. Oh, one thing I will say is, you can imagine with this search here, actually I'll say two things. If we can reduce the state space, so the set of states in some composed machine, we can cut them down a bit, immediately that's going to help us with the search, okay, because these things scale poorly. I think they're bounded exponentially in terms of search time, which sounds bad, but it's not as bad as it could be. Okay, what was the second thing I wanted to say? Yeah, so if you remember back to, say, ESD2, or if you did ADEC, or maybe even in DSD, if you compiled or synthesised some logic for a programmable logic device, an FPGA, and you sat there and it was doing analysis and synthesis, and it was, you're getting frustrated that it's taking so long, right? In essence, it's doing a similar sort of analysis like this, okay? A reduction procedure that is computationally quite difficult, okay? And then mapping that particular optimised logic onto a device is also a similar sort of problem, right? It's almost like a reachability problem, trying to map it in a certain way onto a particular device. That's a hard thing to do. So let's apply it to the traffic light controller. Remember, we explicitly went through depth-first searching. So we went down state by state and ended up with a massive, big, long list of possible states. So, for instance, if you remember, when we observed this state here, because of this self-loop here, right, we've got one state, the joint state, but because this count is increasing and this guard is not satisfied unless count is greater than or equal to 60, we essentially have 61 unique states in there. Extended state machines just hide the fact that there are really a lot of states there, right? We hide it in a variable. Here, instead, with this, with the symbolic model checking, what we're doing is we are going to be writing conditions or the states in terms of logic or Boolean expressions. So I should just be clear. Let's set, so V1 is actually the set of possible states of the, what's V1? Of the light, the traffic light controller. So that would be, for instance, it's only a set of 4, red, green, pending and yellow. And V2 we're going to call the set of states of the pedestrian model. So crossing, none and waiting. So they're sets, right? Now the idea is we can write the set of reachable states in terms of elements of those sets and Boolean operators operating on those things. So for instance, in the red crossing state here, we default with count being equal to 0. So we could write that as V1, the state of the controller, and V2 being red, and the state of the pedestrian model being equal to crossing. And we can also compose that with variables as well, part of the extended state machine. So count equals 0. Now, it feels like that's no better than what we had originally for a depth-first search, right? Because that was one of the states in particular. But here we're specifying it now in terms of logic here, right? Between the conditions of the states in either of the sets. Now, where it gets more powerful is that we are then able to lump things together into the one expression. So we could lump, obviously, right, if one transition, this transition is taken once, we've got another state with count being 1. In the old way of doing it, we would have had another state, right? Here we can uniquely and compactly represent this by just bounding count by 1, right? And likewise, we can encapsulate those 61 states as a simple Boolean expression like that. So we're implicitly writing out all of those states as an expression. So that's a much nicer, more compact way of writing that set of 61 reachable states that way. Okay, so we still have to perform the analysis here. So breadth way, well, we've only got one guard that could be possibly true coming out of that state. And that leads us to arrive at green none and look at the landscape from there. And the set of reachable states from there is firstly count being reset. So we're in green, none, and count is now 0. And if we can imagine in that state, we can see, because of this the self loops here, or the self loop and this loop here, we can see that the counter is ticking up for both of those things. So we have another, family of states from there that can be written as an expression in terms of the variable count. Again, we then, which one do we go here? We'll take this pathway first and go to the pending waiting state, where once again there's the potential for having count between 0 and 60. And then so remember, we're doing this breadth first way of doing things, so then we go back to here and we then go down to the yellow waiting, and there's only a count of 5 there. So where depth first would come up with a massive list of every damn number with every state, composite state, here we just have the neat Boolean expressions, and we can use inequalities to represent variables. Okay, so it looks a lot more compact. So what we're essentially doing is we're building this set R implicitly, okay? So via Boolean algebra. That's why it's implicit. It's not an explicit state. If you want it explicitly, you have to expand all that out in terms of the possibilities there. And we don't have to necessarily use ands. We could use ors as well, or any other logical operators. Okay, so that's the complete set of reachable states there. Then I said before that it's a very difficult problem. This is, once again, a bit of a fake model here, in the sense that we've actually gone and composed the model, the machine, so you can see how it works, the building up of the search. Ordinarily, you don't bother building up a complex machine like that, because if you've got a few hundred FSMs with possibly a few hundred states in them, or maybe just a few dozen states in them, right, the state space is just all over the place, right? It's too complex to draw. So this would be built up via just the independent machines and knowing the connections between them. Okay? So the idea is, well, if we can reduce complexity of the machine, that'll help our search, won't it? Right? If we've got unreachable states in there, no way we can get into them, why go over that search space necessarily? So we should really use the simplest model we can to prove some safety statement, if you like. Because they have smaller state spaces, easy to check, less computation, etc. But here's the real kicker. When you're abstracting stuff, what do you throw away? And what, if you're throwing away something, is it important? Are you throwing away something that could be vital for the safety of the system? And because you throw it out of the model, you check the model and it appears safe, but you've thrown it away. It seems crazy. So which details can you abstract away? That's a really tough question. For instance, my traffic light control state machine back here, it's a traffic light controller, but it has no cars in it, right? There's no cars there. That's already been abstracted out of it, right? There's no need to, because it's just reacting according to some sort of inherent counter, which is a timer, and a pedestrian approaching the crossing. So cars are abstracted out of it. It seems weird, right? You're modelling a pedestrian crossing and you've abstracted cars out of it. Fair enough. So the technique that we use is what's called localization abstraction. And the idea behind that is to take a complex state machine and hide variables, state variables that are irrelevant to the property being verified. What does that mean? Firstly, I'll say it doesn't always work. And sometimes you have to do a bit of a half and half approach, where you do some abstraction, you check something, and then you might have to go back to the full model, because maybe something You found something in the abstraction where you need to investigate in a bit more detail. It also doesn't work because typically when you abstract stuff, you end up with non-deterministic machines. Remember, when you've got an FSM and you are stripping info out of it, essentially, well, the guards become simpler because you're taking information about the transitions away. Typically, you will end up with a machine, maybe it's a one-state machine, right? If you abstract all of it out and it's just got a whole bunch of self-loops on it that are all non-deterministic. Okay, maybe that's too much abstraction. An example of the abstraction for the traffic light controller would be, let's remove that count variable out. It doesn't seem to be related to the safety of whether or not the green light is on for the traffic and someone's crossing at the same time. It doesn't seem to be related. And that damn count variable was blowing up the state space, right? Because it was having 61 states here and maybe 61 there and whatever, and 6 here, whatever it is. It was blowing it up. But if we abstract that out and say, nah, we're just going to just have all non-deterministic transitions here, which, remember, what that says is those transitions are possible, but we don't know when they're going to be taken or why they're going to be taken, but they're possible transitions. Then the machine just becomes a 4-state state machine. That's it. And therefore, it's much easier to analyse. Once again, we already know the answer, that there's no composition where you can have green and crossing at the same time. But this is just the idea, that we've abstracted it all away. But it can cause problems. Sometimes it's really difficult to work out what the relationship between variables and the property that you want to verify. And of course, if you abstract them out, then maybe you will unwisely say the machine is safe because you've dumbed it down too simply, basically. Okay? So typically we do this at a few levels. We may, as an initial check of safety, run it on something like this, right? Build up the reachable set of states and check maybe some condition. This is a condition on the states. And if we encounter a problem, then we're perhaps in a bit of trouble. Then we have to then duck down into detail and maybe go over a trace, go back to the full model and start getting into more complexity. At least we have a rough idea of perhaps the trace which has caused a problem. Right? We've ended up in a state we don't want to go to. Or we could progressively pass this model, pass the safety check. It's never satisfied that particular condition there. Then we can go to a slightly more complex model and slightly more complex and slightly more, and then maybe that's enough checking that we have to do. Okay, so it's really not a one-size-fits-all situation. It's kind of this abstraction thing. There's no set rules to it. This is not a if x is greater than 2, you do this. If it's less than 2, you do that. It's kind of just you feel it out, seeing what the design looks like. Okay, so the other thing about abstracting like this, and people hate non-deterministic state machines. Well, when you first introduce them, you hate them. But this is a fake non-deterministic state machine. It's fake because we know that there is actually real information that is determining those transitions, which one to take. We know, it's there, it's in the model. But when we're dumbing it down, we're making a fake non-deterministic machine, right? In some sense, it's fake. We do have that info. We've just got rid of it. Okay, so, and this is typical when you're doing this reachability test. You will always have these guards, crazy guards all over the place that are just true because you're just showing the transitions possible. All right. So this shows what's reachable, but not how it's reachable. How, you're going to have to do a proper trace on the machine to find out how you get there on the full machine. Okay, so I've said a lot about safety, and indeed probably about That's an ugly 9, but about 90% of the literature and stuff out there tests machines for safety. Safety, if you want to informally state it, says nothing bad ever happens. So the bad was green and crossing, and to state that nothing bad happens, we state it in LTL logic up the top there, right? You can state it as a proposition with the LTL operator. But there's another property that's also interesting to check as well. It's called liveliness property. And you can word it up there saying something good eventually happens. And I'll give you the robot example a little bit later. Now the safety, so that's like about 10% of the stuff out there checks the liveliness property. So safety property is really easy to check. Even for complex machines, you've got heuristics to determine the algorithm to do the search. But the reason why it's easy to check is you've got a finite length counterexample. So if I say to you, for this machine, nothing bad ever happens, and you can find something bad happens along one trace, immediately that proposition's destroyed, right? Easy. You can find a trace, it's a finite length example where you have ended up with a condition you didn't want to happen. So if you can find a counterexample, it's always finite length. Now, the kicker is, for liveliness, it's the opposite. The only counterexamples you can have are infinite length, right? Because the liveliness property says something eventually happens. So the only counterexample you can have is that it infinitely, that it is an infinite proposition, right? Because you have to prove that it can never happen, right? So it's like it's very difficult to check infinite length counterexamples. And that's why model checking liveliness properties is much more involved than doing reachability analysis, like we've seen depth first, breadth first for safety considerations or safety properties. It's okay, we can do liveliness properties, but it might involve flipping some operators around, as we'll see. Okay, let's go back to our little robot, because you know robots are the focus of a lot of the examples in the subject and of course the workshops. So let's go back to this problem here. So I've got a specification for a robot, and I want the robot to pick up some things in any order you like. So there's a grid or something, and it's got to go along and reach, let's say, particular squares that's gridded up. We'll just assume that when it touches the square, it's picked up the thing. That might be easy. And it has to pick that item up. So we'll represent that by phi I. You've got n things to pick up. That's your spec. So your goal to achieve. So you've got to state that in temporal logic, right? So right, the robot picks up item I, and it has to pick up item, phi 1, phi 2, phi 3, phi 4. So we can write that using that. Oh no, F. F is the bad one. F is like a liveliness property, right? Eventually, that's the hard one to do. Eventually, phi 1, and eventually phi 2, and eventually phi 3, etc. So that would be a liveliness property we have to check, right? That eventually all those things are met. What about if we added a bit more complexity to it? What if we wanted the robot now to visit those particular objects and pick them up in a specified order? Well, we can just apply some precedents and nest these LTL statements. So you would say that, eventually reaches phi 1 and eventually reaches phi 2, etc., all the way up to phi n. So that's assuming, let's just do them in order, 1 to n, right? we're implying order. So what we have is we have a nested statement here. You have the inner stuff and you work it out. A nested LTL statement. Okay, so, right, so it kind of implies that perhaps what we could do first is look at how to just do the liveliness property for one particular item, and then we can perhaps compose them more simply if we want them out of order. Let's just look at one, and then would we be able to AND them all together? So liveliness is hard. It says eventually something will happen. That phi 1. Eventually. How long? Who knows? Could be infinite. Who knows? But eventually it will happen. The trick is to flip that F property into a counterexample for the always LTL statement. Okay, so remember this is the eventually. And this is the always. So what this says is that phi 1 is true sometime in the future, eventually, if and only if the opposite of phi 1, so phi 1's false, is always false and falsed again, if you like. So you could say if not phi 1 is always false. It's a bit of a wordy way of saying it. And that kind of makes sense, right? If you want to prove the eventual property, you can prove the opposite always property. And that's good because that turns, once again, this global, right? This is also known as global always, right? That's why there's a big G there. Don't know why that's called F, but eventual. So we can link the eventual and the global like this. F is bad, G is good. That's the easy way of thinking of it that way, right? The G property is much easier to check for. So all we have to do is, if we can find a counterexample to always phi 1 being false, then we have we've been able to check that, the eventual property. Okay? So we've got to find a counterexample to a trace that gets the robot, is a trace that gets the robot to the desired point. Okay, so I will say also that all we need is one. There may be traces that can do it, but we just need one to break it. That's all we need, one counterexample. Okay, we only need one, a counterexample to show, because this is an always property, which is nice, right? We just need to break it once and then we've got a proof. Follow the trace back and we've got the way of doing it. So let's examine a little bit how this can work for our robot delivery service. Right, so back to the robot delivery service. We've got, can I count here? We've got 4 rows and how many columns? 13 columns. Okay, so what we can do is let's represent this. So if you wanted to do a model checking of this system here, you would have your beautifully designed FSM for your robot, and now you also need the environment, a model of the environment, because you're going to compose them into a closed system and you're going to run a reachability analysis over it to check what's going on. Okay? So let's think about the robot. The robot can move left, right, up, down, stay put, so it's just rows and columns it can move, or it can wait in a particular square for an indeterminate amount of time. Okay? Time is not mentioned in here. So we can consider the robot state its position. So immediately you could think, well, it's a grid, it's 13 by 4, you have 52 possible states it could be in. But you could be a bit more complex about it. I mean, do we need to keep track of which direction the robot's facing in? Potentially. There might be a different state which might a variable that holds the value of which direction it's pointing in, right? Okay, so that could blow up, right? You might have multiplicity on that depending on how many variables you want to encode. Do you want a variable to encode the last direction that it turned? So you alternate left, right, 1, -1, something like that. It's going to blow up the state space as well. Okay, but for a very, very simple sort of setup here, right, 52 states would be the obvious minimum amount of states you could have for the robot. Okay, so what's the goal to be achieved? Hey, our good old goal is the F operator, right? Eventually it gets to phi. How long? Who knows? And it could be an infinite trace to get there, right? It could be going round and backwards and forwards, up and down, left and right, all over the place. Very difficult to check. It's a liveliness property. Okay, so what we can do is we can flip this around again in our good old LTL logic. And instead, what we need to do is we need to construct a counterexample. And we construct the counterexample again to G, so globally, phi1 is false. And if you construct a counterexample to that, you therefore prove that eventually it gets... Oh, sorry, that's... We're not doing ordering now. That's just phi. Damn it, I've got an eraser on here. I might as well use it. Okay. That's not too bad, right? You could represent the state. So now if we're doing a reachability analysis, we need to represent the state of the system. Easy, right? The environment, sorry. The environment is obviously, this could be the state of the environment, right? And it's static. Those blocks are at particular locations. And we can then compose some sort of machine together that could represent the environment and the system together. But it can get more tricky, right? So this is a pretty simple setup, right? Static objects, you a priori know where they are, so you could almost always just, you know, pick a path, any path. Well, that's probably the only one to work on. You obviously go this way, right? But you could determine that a priori almost and just go forward, 3, turn left, up, 4, whatever. You could rely on your bump sensors and things like that too if you don't know it beforehand. So to find the path of the robot, well, you have to do a composition of these things and do a reachability analysis to see that you can actually eventually end up here by finding a counterexample to that. But let's make it a bit more interesting. Let's have some nefarious obstacles here that can now move to try and maybe block the path of the robot as the robot moves along. Or you could think of some primitive computer game where things are moving, you have to get your timing right to go underneath them or through them. So now the robot can move in its usual way, but the environment obstacles can just move up and down. They can't change columns, they can just change rows. Okay? Wow, the complexity of this system is now crazy. Think about just the environment. Forget about the system. The environment now has reachable states, a lot more, right? This is only a static state here. This is now has movement, so you've got a ton of reachable state. Well, not a ton, but quite a few reachable states here. So let's make it simpler. Let's just allow the environment to react 3 times. So the environment, you've got 3 moves and 3 moves only to stop this particular robot from getting to the other side. Okay, so for instance, you could do one strategy, right, of the environment. Now the environment would be trying to block this, right? If the robot, it depends on the rates of movement of these blocks versus the robot, who reacts first and such. But you can construct a counterexample, right? You could formulate the environment machine now, which is an FSM, which has a lot of complexity to it because imagine all the combinations of moves you can have there. It's like a damn chess game. And then the robot, which is just chugging along. You have to construct a counterexample. Luckily, you could look at this, because it's a simple system, believe it or not, and construct a counterexample. If you're allowed 3 moves, if you moved, say, so what's going on here? If you move that one across 1, that one down 1, and across 1, that would be, are we allowed to move across? No, whoops. I'm cheating. I don't know, I'm trying to find what's the strategy for that goes across, that blocks it that way. Or this could go down too or something. I don't know. There's probably a way of doing it somewhere in the middle here. I should have probably worked it out before. I did it visually. So if that goes down 1, that goes down 1, that goes up 2, that's too many moves, isn't it? All right, help me out here. There is not a solution? Yeah, I thought I blocked it before, but
There isn't one. There's in 5 moves.
Yeah, I can do it in 5. I'm just wondering if it's restricted to 3, if it's possible. Not without changing columns, right?
You can do it with 5 without changing columns.
Yeah, easy, yep. Interesting. Open question. What's that?
So the third block from the left
Yeah.
was right 1 time.
Can't change columns.
Oh, you can't change.
No, it's just up, down, or stay put. So that's interesting, because in my head I quickly did, and I thought, oh yeah, just move those across, and now I realise it doesn't seem to work. So interesting, isn't it? That this is not a robust way of checking whether or not this is a feasible system, right? In order eventually that it gets to phi. And I didn't even think about the robot moving, right? I'd have to work out the reactions of the robot versus the reactions of the blocks trying to move. Once again, you could then, if we wanted to do an analysis, right, to say, well, can you do it with 3 movements of the obstacles, 2 movements, 5 movements, 4 movements? With a proper reachability analysis with the full state space, you could properly do that, right? So how do you find an environment policy to prevent phi from happening, right? So eventually reaching that square? Well, you need to construct that counterexample, right? Well, in order to prove that you can't make it there. So you have to find a state that can do that. So you've got to construct a counterexample to, we want to prevent it. So we want a counterexample to eventually get there. So we need to find a counterexample of eventually getting there. Yeah, I'm glad I stuffed that up, because it kind of nicely shows you with these sorts of things, you can't just sit there and go, oh, I think I've tried most things. It looks like I can't do it. You need to run it through a proper model checking tool. If you're interested, if you want, go and Google SPIN. SPIN is a formal model verification tool. It's free. You can download it from multiple platforms, compile it, play around with it and all that sort of stuff. So that might, if you're really interested, give you an idea of what a real verification tool looks like. And you could populate it with some very basic FSMs and see how it composes and checks reachability of those machines. And that is a very good example why we let computers do this and we don't try and muck around and analyse it ourselves, because it's just too damn hard to do without making mistakes. All right, I think I'll leave it there. Please go back over the breadth first way of doing things symbolically, because it is an exam question, which I'll talk more about the exam later on in week 12, but it's good to nail it now. All right, download SPIN, it's free. It's got some interesting papers and stuff you can read about it. Next lecture, we're going to do quantitative analysis. We'll do a bit about cyber security, which is hugely important for embedded systems, and then we've got review and exam. Okay, got questions? Come on down and ask me now.